Alright guys, so now that we've looked at a couple things and how energy works, we're going to go through a few definitions and show you some calculations with this. It'll be very important when it comes to your lab that you're going to do. Alright, so it'll be very important when it comes to your lab you're going to do. So first let's look at the definition of energy. Energy, once again, is the ability to do work or produce heat. Alright, so if you're doing work or producing heat, as I'm lifting this pin up and down, I'm doing work. Okay? Even if I sat there and did nothing, I still would have energy because my body is producing heat. Alright, next one down. Too far down. Here we go. Alright, next one we have heat. Now, there is an equation we're going to be using, and heat, the variable for it is Q. Alright, Q is the variable for heat. So heat is a form of energy that flows from warmer objects to cooler objects. Okay, warmer objects to cooler objects. That is what heat is. So again, as you're watching this, if you need to write these down, pause it, and then push play when you get it back. Alright, next definition is temperature. Alright, a few minutes ago we were measuring the temperature of water. So what is temperature now? This is an interesting definition. Temperature is a measure of the average kinetic energy of particles in a sample. Average kinetic energy. Again, energy or temperature is energy measure the average kinetic energy. What is kinetic energy? Kinetic energy is energy in motion. So, what does this mean? Well, let's look at something like a solid. If you remember, solids, all right, are pretty far packed in. Now, do solids have a temperature? Of course solids have a temperature. So that means they must be moving because temperature is a measure of average kinetic energy. So they are vibrating back and forth, but they're pretty packed in. Let's look at liquids. Liquids are a little more spread out. That's what makes them a liquid, right? And they're flowing over each other and moving. So their kinetic energy is a little higher. So what does that mean about its temperature? Well, compared to a solid, a liquid's temperature should be higher. Why? Because its average kinetic energy is higher. Ability or its movement. And last we have gases that are way spread out and flying around. Right now you have all kinds of gases smacking you in the face. Alright? Gases are spread out, moving around very quickly. So their average kinetic energy must be high. So their temperature must have a higher temperature. So if I look at a solid to liquid to gas, we are increasing temperature because the kinetic energy is increasing. Alright, next word is specific heat. Now I'm going to talk a little bit more about specific heat. It's part of an equation we'll be using, so I'll just let you get this down. It's the amount of heat required to raise the temperature of 1 gram of any substance 1 degree Celsius. To try to make this easier for you to understand, it's like this. If I had a gram of water in my hand, so 1 gram of water in my hand, and let's say the temperature of the water was 20 degrees Celsius. Okay, so the temperature is 20 degrees Celsius for this 1 gram of water that's in my hand. The amount of energy it takes to take it from 20 degrees Celsius to 21 degrees Celsius, okay, so from 20 to 21, so 1 gram goes up 1 degree Celsius, the amount of energy it takes, that's a substance's specific heat. Okay, every substance has a different specific heat, and depending on the state of matter it's in, it also has a different specific heat. Alright, next, we've talked about all this energy stuff. Well, like most of chemistry, when we talk about a new topic and we talk about calculations, things need units. So what's the unit for energy? Well, the unit for energy is going to be joules, okay? So a joule, J-O-U-L-E, joule, abbreviated capital J. Okay, so a joule measures energy. Now there's another unit we will use and talk about a little bit in here, and you're more familiar with this one. Alright, now there's two forms of it. We have calories, and notice this is little c calorie. Alright, little c calories. And then we have big C calories. So, big C calories. This is what you hear all the time. Big C calories are nutritional calories, what you see on bags of barbecue potato chips. Alright? So, big C calories, little c calories. So joules is what we'll mostly mess with. And how do you go from joules to little c and big C calories? Well, 4.184 joules is equal to 1 little c calorie. And 4,184 joules is equal to 1 big C calorie. All right? So there is your conversion. With all that being said, what we want to do now is make sure you are prepared for your lab. So we're going to go back and talk about what was happening with the water that was being heated up. So I've told you that energy, when it goes into a substance, is going to do one of two things. It is either going to change the temperature of the substance, or it is going to change the state of matter of a substance. So what I'm going to do is show you a graph. All right? Now here's our scenario. Let's say we have a cube of ice. Okay, we'll just deal with water for right now because we're familiar with that. So we have a cube of ice, and let's say we know the freezing point of water is 0 degrees Celsius. So let's say our ice is colder than that. We'll say it's negative 10 degrees Celsius. Okay. So we're going to say we start at negative 10 degrees Celsius, and our temperature is going to go on our y-axis here on the graph. So we're at negative 10 degrees Celsius to start with. All right, we're going to add energy to it. Right now, it doesn't really matter how much energy we add as we look at this. All right? But we're going to add energy to it. So energy is going to increase as we go this way. All right. So as we add energy to this block of ice, what will happen is if I was graphing the amount of energy and the temperature, as we increase the energy, the temperature would go up. And it would go up and go up and go up. Now, there's a point in which it will stop going up, and all of a sudden our graph will actually level off. Meaning, we're still adding energy, but look what happens to our temperature. It stays the same. Why does it stay the same? Well, I just told you. Energy is going to go in to do one of two things. Either raise the temperature or change the state. Well, what temperature do you think this rises to? If you said 0 degrees Celsius, you're correct, because what happens to ice at 0 degrees Celsius? It starts to melt. And so what you'll see in the graph is, you'll see the temperature go up to 0 degrees Celsius. So if I had a thermometer and stuck it in some ice and started giving energy to this ice, temperature would go up and up until it started to melt. And when it starts to melt, the temperature doesn't go up anymore, but energy is still being inserted into the ice, which now is becoming liquid water. It will continue to happen until it all becomes a liquid. And then what happens? Well, if I continue to add energy, the temperature is going to go up and up and up and up and up and up and up to a point. And then guess what? It starts to level off again. Well, now we're dealing with liquid water here. So we were at 0 degrees Celsius. We keep heating it up until, well, at what point is going to stop heating up? What point? What temperature? If you said 100 degrees Celsius, you are correct. At 100 degrees Celsius, what's going to happen to water? It's going to start to boil. All right, so our water starts to boil. So once again, our temperature is going to plateau, meaning the energy that's being added all goes to boiling the water, changing it from a liquid to a gas. Once it becomes a gas, if you can still heat it up and you have a thermometer in there, the temperature will just keep going up and up and up, depending on how much energy you added. All right, so this is what a graph would look like if I, once again, had a thermometer and ice cube, heated it up and wanted to keep heating it up to a certain temperature all the way to when it becomes a gas. Your graph would look something like this. All right. With that being said, we're going to look at a nicer version of this graph. Now, to figure out how much energy is being added as we go along this graph, there are lovely equations for it. Basically, you have three equations. All right, as you're increasing the temperature of a substance, the equation you use to figure out how much energy is being added is Q equals mc delta T. In just a second, we'll talk about what all those mean. So Q equals mc delta T. You can see as our graph goes up in temperature, All right, so our substance is being heated up and the temperature is rising. You can use Q equals mc delta T to figure out the amount of energy. Now, a second equation you can use is on this plateau here. Now, if you remember this first plateau, we were going from a solid, this is a solid right here, to a liquid. We're going from a solid to a liquid. So from a solid to a liquid, all right, we call that melting. And if you go backwards, because you could go backwards, we could, instead of adding energy, you could lose it. All right? What do we call that? Well, we call it freezing. So, right here is our equation for not when we're raising the temperature, but when we're changing states. It's delta H. Delta H stands for enthalpy, right? And this is called the enthalpy of fusion, or another way to say that is heat of fusion, okay? So you can call it enthalpy of fusion or heat of fusion. All right, so if I want to figure out how much energy has to be added just to melt our block of ice, you just take the mass of the ice times this delta H of fusion. This number, right, this variable will be given to you. All right, you'll be given this every time. So all you do is take the mass times this number that's given to you to get how much energy it takes to melt our ice. All right here you see another Q equals mc delta T. So once again, we're heating it up. All right, this is our third equation. I told you had three. Q equals mc delta T. Delta H equals mass times delta H of fusion. That's what this little FUS stands for. This is our third equation. It's going to look very similar. This is delta H equals mass times delta H of vaporization. Right here, we're going from a liquid to a gas. All right, liquid to gas. What do we call liquid to a gas? Well, it's called vaporization. There's two types. The type you saw in the video already, boiling, and a type you're familiar with also, evaporation. Okay, both of those are vaporization. So, how do you figure out how much energy it takes to boil all of our water? So however much water you have, well, you take the mass times the heat of vaporization, the heat of vaporization. This number will always be given to you. Right? What we call this equation, right, is called the enthalpy of vaporization, or another way to put it is the heat of vaporization. Right? So your three equations, I'll go back over them, are Q equals mc delta T. Anytime the temperature is changing, you use Q equals mc delta T to find the energy that is given off or taken in. Anytime you have a change in state, if it's a change in state from a solid to a liquid, we call this the heat of fusion. Your other equation, if you go from a liquid to a gas or a gas to a liquid, this is called heat of vaporization. Those are your three equations. Now,